solve another Leetcode problem, 820, sort encoding of words. So we are having an array of words. So for example, we have this time, me, and bell. And we want to have such kind of encoding. So for example, this time, you can check that. So this time, it is end with me. And for this me, it is also okay. So we don't need to encode another me. Yeah, let me just copy it. Yeah, so this is because this is like a suffix string problem. Yeah, because for this time, it is add with me, so we don't need to encode it anymore. So this is still okay. So for example, if there is a IME, it is also okay. If there is ELL, it is also okay because it is ends with ELL. Yeah, because bell is ends with ELL. And we're going to return the length of the shortest reference string as possible of any valid encoding of words. Yeah, so this means we're going to return the shortest. So the shortest for this example, time with a hash and bell with a hash, it is 10. Yeah, so let's try to understand the problem. So a valid encoding of an array of words is any reference string. So that is a string S and array of indices. So there's a meaning for this indices and the encoding of the string S. So the first index is 0, it means I'm gonna start with 0, I have a word, so it is the time. And another encoding 2, it means I'm gonna start with index 2, it is me, it is also okay because it is adds with a hash. And for index 5, it is okay because it is bell and it adds with a hash. Yeah, so from this kind of example, basically we want to find some intuition of how to solve it easily. Basically, this is a suffix tree problem. Yeah, but the suffix tree is difficult. So we're going to use the prefix tree to solve the problem. So first of all, we're going to prepare the encoding. So we're going to reverse the words of time and bell. So for example, we're going to reverse it to emit and LLEB. We're going to reverse those two words. And then we're going to put it inside a prefix tree. So for a prefix tree, from the beginning, there's an empty. Let's just say this is a root. So from the root, we have the letters E, M, I. Yeah, let's say I and T, right? So this is a T. Another one is, so for example, this is L, and still L, and goes to E and B. Yeah. Now we are going to check this prefix tree. So for this E and M, it is okay, but we will not count it. We will count it until to the tail. So we're gonna count it as emit. And another one is LL and EB. We're gonna count it as LLEB. We're gonna count the tail. We're gonna count from the root until the tail of the prefix tree. So this is a tail, this is another tail, so we're gonna count those two tails, and one of the tail gonna plus 1. So the tail for this word is 4 plus 1, it is 5, and for this one it is also 4 plus 1, it is 5. Yeah. Now let's try to solve it. So as it is a template problem, basically I'm gonna just copy some of the template from the Trie. Yeah. So the basic template may be from here. Let me copy the template. Yeah, you know, I don't need to code it every time. Basically, the template gonna be. Yeah, I also need to define a Trie node. I forgot to copy the Trie node. Let me just define the Trie node. So for the Trie node class, we're gonna prepare children and add of a word. So self.children should equal to dictionary, and self.add of a word should equal to false from the beginning. Yeah, so basically this is the basic template. And then we're gonna initiate the try, and we're gonna have some method for the insert. Definitely we're gonna use the insert, and for the search and start with, definitely we will not use it. Yeah. So I'm gonna delete it. Now, we can use the try and data structure to solve the problem. So we're gonna prepare a t should be equal to try, and then we're gonna make the words to be a set of words. So it's gonna be the set of words, and then I'm gonna check one by one. So for word in words, so we're gonna insert it. So t dot insert with the words, but we're gonna reverse it. Yeah, because we're gonna check the suffix tree, but we're gonna turn it into a prefix tree. Because prefix tree for a trie is easier. It is much easier. We can directly use the trie data structure to solve it. Yeah. Now we insert each of the word inside a trie, and then we're gonna check it. So for word, still inside the words, the set of words. And let's say we're gonna define another data structure, another method. So let's say it is a tail of a word. If it is a tail of word, I'm gonna return true. Otherwise, I'm gonna return false. So let's define a tail of word. Yeah. Let me give a pause at the moment. So currently, we're gonna use this kind of method. So yeah, if tail of this word, yeah, still we're gonna reverse it. If this is a tail of word, so the result would plus equal to the length of the word plus 1. Finally, we're gonna return this result, and we also need to prepare a variable result. Starting, it's gonna be defined as 0. Yeah, now we're gonna try to write this method tail of word. So inside a trie, we're gonna check if it is a tail of word. So this is gonna be easier, just like the insert. So we're gonna prepare a current. It should be equal to self.root, and then we're gonna check each character inside the word. So for say in word, but here we don't need to check that, because if we insert all the characters inside a trie, definitely it exists. Yeah. So it means it is different from here. So for here, the current should equal to current dot children with this character. And finally, we just need to check if length of current dot children, if this dictionary equal to 0 or not. If it is equal to 0, it means it is the tail of a word. So for example, we're gonna check the word one by one. So first of all, we're gonna check E, and then we're gonna check M, and then I, and finally we're gonna traverse this character T. But for T, there's nothing inside, so the dictionary gonna be empty. Yeah, so the current dot children, it is a dictionary, and this dictionary should be empty. So if it is empty, it is a tail of word. So if it is not, so for example, EM, it is EM for this me, ME. Yeah, so for this EM, it is not at the end of the word, so we will not count it. We only count the image. We will not count EM. Now, let me just run it to check if it is okay. Yeah, because I need to use the method t.tail of word, because this t is a class, it is a trie class. I'm gonna use the method. Yeah, as you can see, it works. Now let me submit it to check if it can pass. Yeah, as you can see, it passed and it's pretty fast. Now let's analyze a little bit about the time complexity. The word's length is 2000. So let's say this is the length of the word, it is n. And we're going to initiate a trie, and we're going to insert the word, each word inside a trie. So the time complexity for here, how many words? 2000 words, and the length of the words is 7. So it is 7 times 2000 up to here. And then we're going to check each of the word. So for each of the word, we're going to check if it is a tail of a word. Yeah. So this is going to still be it's gonna still be the same. Yeah, basically, this trie, the depth of the trie can only be 7 because the length of the words is 7. Yeah, so we're gonna traverse each of the word. So there are 2000 words, and then we're gonna check. So the length is 7. So it is 2000 times 7. So this is gonna be the time complexity. So let's say this is m and this is n. So the time complexity gonna be m times n. Thank you for watching. See you next time.